What is VulChecker? So VulChecker is basically kind of a spell check for vulnerabilities and bugs in source code. So what do I mean by that? So if we look at this small code snippet, we see here a vulnerability, which is a use after free vulnerability. And you can imagine as a developer, the root cause and manifestation point can be thousands of lines of code between them and make it very hard for the developer to identify these flaws and these bugs and vulnerabilities. So what we'd like to do is we would like to highlight inside the IDE itself, kind of like as you would with Word, a small little red squiggly line that would identify exactly where manifestation points are for particular CWEs, so the developer can then fix his bugs or vulnerabilities. So there's a few advantages for that or reasons for that. First being, of course, we'd rather not ship software with bugs and vulnerabilities out into the wild. And the second is that if we have some sort of source code project out, let's say in GitHub, that we want to include inside our system, we like to scan it and look for vulnerabilities beforehand. So VulChecker uses deep learning in order, or graph-based deep learning in order to identify these vulnerabilities. And when we did our survey of other approaches for identifying vulnerabilities in source code, we identified a few different issues. And the first one is localization. A lot of these methods, what they do is they take a large region of code or entire function, they represent that some way for machine learning and pass that to the model and ask it, is this piece of code vulnerable or not? And the problem with that is that once the model says, yes, this is vulnerable, you have no idea where inside this chunk of code to look. So if you highlight this entire region and give it to the developer, now he has to search through there, find the manifestation point, which can take hours, and it could even be a false positive. The second issue is the representation used in machine learning. So there are lots of works which will use tokens from the source code itself and then represent that directly, ignoring the structure of the code or the instructions behind them. Or if they use the graph-based deep learning model, they'll use some basic graph-based representation of the program, which is not conducive for graph-based machine learning. And thirdly, the last issue is if you're building a classification model with deep learning, you have to have a labeled data set. And getting a labeled data set of many, many different vulnerabilities for every single CWE, especially down to the instruction level, identify where the manifestation is incredibly expensive and hard to do. So the contributions that we have in this work are, number one, we provide a method that enables us to point at exactly the line where the manifestation point happens, so the developer doesn't have to waste time trying to figure out where to look. Second, we provide an improved representation for graph-based neural networks for looking at software. And third, we offer a method for data augmentation so that you can take synthetic samples, let's say from the Juliet data set, where you just have a few lines of code just representing a simple vulnerability, augment that in a way so that you can now identify real vulnerabilities in the wild. So let me show you exactly how VulChecker works in terms of execution. So we look at one CWE at a time. So like, for example, here, CWE 416. So we take our source code, we lower it down to LLVM IR, and we extract to PDG. And we look for every single kind of, every single manifestation point, every potential manifestation point for that CWE, for example, malloc. And then what we do is for each of those potential manifestation points, we traverse the graph backwards, and we cut a subgraph there. And why this is incredibly important is now that each of these subgraphs are going to be a sample that I'm going to pass to my machine learning model, and they are all going to be anchored on that specific manifestation point. So if I'm using graph-based machine learning, all the information that the model is looking at is going to flow down to that potential manifestation point. I can then add all kinds of graph-based features on the edges and on the nodes, and then pass that to a graph-based deep learning model to make a prediction whether that graph or subgraph is vulnerable or not. In our case here, we use structured DVEC. So once the model says, yes, this subgraph is vulnerable, we can then look at debugger symbols that we have embedded in our graph and trace that all the way back to the source code and highlight that for the user. So what I'm going to do now is going to pass it over to my colleague here who's going to talk about how we bring the source code down to a lower representation and the first several stages after that.
Hi, so let's start by diving into some of the details of VulChecker, and we'll start with the data representation. Software in its natural form in source code is not really amenable to machine learning. There have been many prior work and actually current work now with LLMs trying to use source code in its natural form. But ultimately, they run into issues for really precise tasks like vulnerability detection because they fail to expose important features upon which machine learning systems need to learn in order to accurately and without false positives detect vulnerabilities. So our key insight is that programs are inherently graph-like. They consist of control flow graphs, data flow graphs, dependency graphs. So why not use graph-based ML on a graph representation of the program? So to take source code and turn it into a program dependency graph to make that amenable for machine learning, we end up using compiler infrastructure, but I want to first talk about what a PDG is. So a PDG is a directed graph where instructions in software are represented by nodes. Data flow and control flow dependencies between those instructions are represented as edges. Now, naively using PDGs, essentially the shell of a program's control flow graph and data flow graph, has been used before. Ultimately, the results were limited because it, once again, failed to expose important features necessary for learning on specific tasks. So our solution to this is to enrich the PDG with embedded features on both nodes and edges to help the machine learning models learn specifically what types of patterns represent vulnerable code and what does not. So for example, if you take a look on the right side of the screen, you'll see a sample PDG corresponding to this very short snippet of code. Each individual node has features embedded within it that designate a discrete operation for that instruction, data types operated on it, static values, and many others. You'll also notice that the edges, depicted in blue, which are data flow edges, are also embedded with feature information about the types of data they carry forward throughout the program. So how are we actually generating ePDGs? Well, we don't want to do it from source code. Source code is abstract. It's meant for people to read and write. And ultimately, this means it contains a lot of useless information for machine learning. We don't care what variable names are. They have no bearing whatsoever on actual software vulnerabilities. We don't care about syntactic sugar. There's 5 different ways to generate a loop, but when you use a compiler and the binary, they end up becoming back edges and nothing more. So we need to be able to clean and simplify our data to make it amenable for machine learning. And it turns out compilers are really good for this. Compilers are natural data cleaning, preparation, and labeling tools when you're using software as data for machine learning. They contain a large number of built-in optimization and analysis passes that actually support machine learning operations when they're retargeted. But I want to be clear, there's still a tremendous amount of effort that we had to do, or the amount of engineering effort that we had to employ in order to get these PDGs generated from LLVMIR to function well with machine learning. So first, indirection and interprocedural boundaries within programs create what are called partitioned graphs, where chunks of nodes are not connected to each other. So we need to connect these graphs because the graph-based machine learning models often employ message passing to pass information forward, and without edges to pass that information forward, you're not able to effectively learn. Fortunately, the compilers expose optimizations like aggressive function inlining and branch expansion that help us eliminate these edges and get back to connected graphs. So now that we've talked about how we've produced the ePDGs, let's talk about how we generate samples. VulChecker conceptually treats vulnerabilities in source code as subgraphs. And these subgraphs are marked and excised from the PDG by marking potential manifestation points and potential root cause points. So stated very abstractly, the root cause point in a program for a vulnerability is the program point at which the vulnerability's conditions are set for it to manifest later in the program. The manifestation point is the program point where the vulnerability is actually triggered or its effects become apparent. Let's look at a couple examples. For stack buffer overflow, the root cause is the creation of a statically sized memory buffer, and manifestation points, and once again, these are potential manifestation points and root cause points, are when you actually write to memory, or instructions that write to memory. For use after free type vulnerabilities, the root cause points or potential root cause points are calls to functions that free memory, and the manifestation points are instructions that access memory. So ultimately, as Yisroel described earlier, we perform a backward slice through the ePDG to collect subgraphs from starting at the manifestation point as the anchor and then back tracing to potential root cause points. When we train data, which we train with the same pipeline that we use for processing software for querying the model later, we simply mark potential root cause and manifestation points as true, false actual root cause, actual manifestation points. This allows our machine learning algorithm to learn from both positive and negative examples of subgraphs. So before we move on to how the graph model is actually trained, I want to spend just a brief moment talking about some of the features that we extract within the PDG. I mentioned a couple of examples earlier, but I want to give some general guardrails and guidance for how to select these features. Prior efforts have tried to take token streams or tried to use ePDG or PDGs naively, and ultimately they had results that were fairly limited. Once again, the cause of this is failing to expose granular and discrete features upon which machine learning algorithms can learn about the specific task at hand. So we selected our features to be relevant to this task, and fortunately many of them were common to the high profile or the high impact CWE types that we originally evaluated. So a couple of examples. We use machine opcodes or machine operations for each instruction. This is particularly important when detecting integer overflows because only some operations on integers can actually result in an overflow. Many cannot. All right, with that, I'll hand it back to you.
Thanks. All right, so the last thing I want to talk about before showing some results is how we do the data augmentation. So again, once again, you want to build a data set that you can train a model on that will generalize to samples in the wild, but at the same time, you don't want to go through the effort of collecting those samples. You rather just take a free data set such as Juliet, which is very synthetic, few lines of code, just capturing that vulnerability, but use that to train your model. So what we do is basically, here's our, for example, our samples of Juliet. We take one sample, and we take a project from the wild, some GitHub project, and we assume that it's clean. We'll check that there's no CVEs associated with it. And what we'll do is we'll extract both PDGs, and we'll splice the PDG, or the ePDG in this case, of the Juliet sample into the project, looking at something like this, that still maintains the same flow of the control flow and dependency edges. And as a result, when we pass this project over to our machine learning model, it's forced to look for the same patterns, but amongst a lot of noise, right? It's just the same kind of concept we do with image-based augmentation for deep learning. So now the model is going to be used to looking through lots of irrelevant instructions, perhaps thousands of instructions apart, but to look for the same patterns it's seen in these synthetic data sets. So for our evaluation of performance, we compared against region, line level based detectors, as well as commercial SAS tools. We used a number of projects containing 35 CVEs. We obtained excellent results compared to state of the art. But more interestingly, when we compare it to a commercial SAS tool, as you can see here for Helix QAC, they found there were 4 true positives with 478 false positives, and if we tune the threshold of our model into the same false positive rate, we can identify 24 true positives. But it's not great that we have a lot of false positives, right? You don't want to have have the developer sift through lots and lots of mistakes. So to understand the precision, what we did is we took 9 different projects from GitHub, we passed it through our VulChecker, and we ranked all the thousands of manifestation points from the most likely vulnerable to least likely vulnerable. And we gave the top 100 to an analyst and said, which one of these are bugs and vulnerabilities? So it turns out that the top 50 results had a 50 to 80% were true positives. And of the top 100 results, there were 45 to 70% were true positives, which is a very high success rate. And of that top 100 results, we saw 17 verified CVEs, and we identified 1 zero-day. The last thing I just wanted to show is the importance of the augmentation. So this graph kind of shows you the embeddings of the neural network when looking at samples that are vulnerable from the synthetic dataset in red and not vulnerable from the synthetic dataset, which are in black. Now, when you take samples from the wild after the model's been trained, and you pass it through this model, which are those in the gray, you can see the model has no idea what these are. It doesn't know if it's vulnerable, non-vulnerable. It's a completely separate cluster. But when you take this model and train it on the augmented data, now it can recognize those augmented samples and is able to put them in the appropriate concepts. So to conclude, just a few takeaways. The first main takeaway I would say is that if you're using deep learning for cybersecurity, in particular for software, just make sure that whatever your input is into the model is anchored on a specific point so that when the model makes a classification, you know exactly what it's talking about. You don't need to turn to explainable AI or anything like that to try and understand the result. And the second part is that if you're going to be working with source code, make sure you bring it down at least to some sort of intermediate representation so that not only you can improve your performance, but also you can enable augmentation as we did here. And if anybody wants access to the source code, you can find it on GitHub. We also have a virtual machine available so you don't have to install anything. And yeah, I'm open to any questions.
Thank you.